name is Pranay and my project is called Modeling Drug Carrier Interactions Using Machine Learning Interatomic Potentials, or MLIPs. In simple terms, I use machine learning to understand how drugs stick to or interact with their surroundings, like water or potential nanocarriers made of carbon. By doing this, we can predict how a drug behaves before it's even tested in the lab. The goal is to design drug delivery systems that are faster, safer, and more effective. When a drug enters the body, it doesn't go directly to where it's needed. It travels, interacts with different molecules, and often relies on a carrier to reach the right spot. The way a drug attaches to its carrier decides how stable it is, how long it stays there, and how efficiently it's released. If the interaction is too weak, the drug might fall off early. If it's too strong, it may not release when it should. Studying these interactions helps scientists design smarter carriers that deliver the right dose to the right place. Before testing carriers, it's important to understand how the drug behaves in water. Water affects how well a drug dissolves, and that directly influences how it's absorbed in the body. If a drug isn't soluble enough, it won't work properly, no matter how advanced the carrier is. By looking at drug-water interactions, we can predict solubility and figure out what changes might help a drug perform better. Ibuprofen is a familiar painkiller and part of the group called NSAIDs, which is short for non-steroidal anti-inflammatory drugs. It's safe and effective, but one major drawback is that it doesn't dissolve well in water. That limits how efficiently it can be absorbed. I chose ibuprofen because it's a great example of a drug that works well, but could be improved with better delivery methods. Understanding how it interacts with water and with possible carriers can point us towards those improvements. Aspirin is another common non-steroidal anti-inflammatory drug and one of the first synthetic drugs ever developed. It's used to relieve pain, reduce fever, and prevent blood clots. It dissolves a little better in water than ibuprofen, but it can irritate the stomach if taken too often. Because aspirin and ibuprofen are similar but behave differently, comparing them helps show how molecular structure affects binding and solubility. For a possible carrier, I studied carbon fullerene, often called C16. It's a hollow, soccer ball-shaped molecule made entirely of carbon atoms. It's strong, lightweight, and stable, which makes it interesting for both materials science and medicine. In drug delivery, its structure could help trap or hold molecules until they reach the right place in the body. To understand these molecular interactions, we need to calculate the energy and forces involved. Quantum mechanical methods can do this accurately, but they take a lot of time and computer power. MLIPs solve that problem. They use machine learning to make predictions that are almost as accurate but much faster. That makes it possible to test large molecules and simulate longer interactions that would normally be too slow or expensive to compute. Here's the basic idea. We feed the model the positions and types of atoms in a molecule. The output tells us the total energy and the forces acting on each atom. From there, we can figure out how the atoms move, how they settle into stable shapes, and how strongly two molecules might attach to each other. This makes MLIPs powerful tools for studying chemistry in a virtual environment. These MLIPs use graph neural networks, which think of molecules like connected webs. Each atom is a point, and each bond or nearby atom is a line connecting those points. This setup helps the model understand not just individual atoms, but how their relationships affect the whole molecule. It's a smart way to represent chemical systems. One important thing about molecular modeling is that math has to make physical sense. The total energy of a molecule shouldn't change just because we rotate it or move it somewhere else. That's called being invariant. Forces, on the other hand, should shift in the same way the molecule moves. That's called being equivariant. These rules make sure the results we get actually reflect real chemistry. Before we look at how molecules interact, we need to make sure one is in its most stable form. That process is called geometry optimization. The model adjusts the positions of atoms until the total energy is as low as possible. When energy stops changing, that structure represents the most stable version of the molecule. It's like letting the atoms settle in a comfortable resting position before seeing how they behave together. This step matters because if the structure isn't stable, everything that comes after would be inaccurate. Optimized structures make sure our binding energy and stability calculations reflect reality. Without it, we'd be comparing unrealistic shapes or distorted molecules. There are two types of energies that help describe how molecules behave. Atomization energy tells us how much energy it takes to completely break a molecule into its individual atoms. Binding energy tells us how strongly two parts of a system are attached. For example, if a drug binds tightly to a carrier, it means a lot of energy would be needed to separate them. By calculating these energies, we can measure how stable and strong molecular interactions are. These energies aren't just numbers, but they help us understand how stable a system is, how strong the bonds are, and how easily a drug might attach or release from its carrier. In drug design, we usually want a balance. The drug should stay attached long enough to travel safely, but not so tightly that it can't be released when needed. Now let's look at the results. When ibuprofen interacts with water, the binding is fairly weak. This means the two molecules don't interact with each other very strongly and explains why ibuprofen doesn't dissolve easily. In other words, if molecular structures resist forming stable interactions with water, which matches what we already know from everyday use. For aspirin, the interaction with water is a little stronger. It forms a slightly more stable bond, which helps it dissolve more easily than ibuprofen. This shows that even small changes in molecular structure can have a noticeable effect on solubility and absorption. When aspirin is paired with carbon fullerene, the binding becomes noticeably stronger than it was with water. This means the fullerene surface can hold aspirin molecules more securely, which could make it a good candidate for carrying the drug in nanomedicine applications. Next, I tested what happens if we replace one carbon atom in the fullerene with boron. This small substitution makes a big difference. The bond between the drug and the carrier becomes much stronger. This suggests that adding boron could improve how well a carrier holds onto a drug, which could also lead to more controlled release systems. However, when I replaced the carbon atom with nitrogen instead, the change was minimal. The strength of the interaction stayed about the same as the original fullerene. This shows that not all substitutions have a noticeable impact and that boron specifically plays a stronger role in enhancing drug binding. All the results are measured in electron volts or eV. 1 electron volt is the energy an electron gains when it moves through a 1 volt potential difference. It's a small amount of energy, perfect for describing interactions that happen at the atomic or molecular scale. To wrap up, using MLIPs made it possible to predict how drugs like aspirin and ibuprofen interact with water and with carbon-based carriers quickly and accurately. The results showed that aspirin binds more easily than ibuprofen, and both attach moderately to carbon fullerene. When boron replaces one carbon atom, the binding energy becomes significantly stronger, but nitrogen substitution doesn't change much. This approach helps identify which carrier materials could work best before doing expensive lab experiments. The structures we model were stable, which means the results are reliable. Going forward, I plan to include temperature and solvent effects to make the simulations even closer to real biological environments. Thank you.